Okay, let's start. So, in the last class we looked at a two-stage Miller compensated OTA. So, this is our two-stage OTA. Here, as we know, if you don't do anything, the two poles could be very close by. So, to basically split the poles, what did we do? Yeah, what did we do for Miller compensation? Yeah, I put a cap. Basically, we put a cap across the second stage GM. So not this cap, right? So we'll put a real capacitor. So this was the cap CC. So yeah, let me do one thing. Let me actually write the things clearly. So let us say these are the intrinsic conductance capacitance, and on top of it we have the load conductance capacitances, and together we club this and call it GL prime, and CL prime includes both CL and C2, right? So here, as we saw, there were two poles and one right half plane 0. So I can write the transfer function as A0 into 1 minus S by Z1 by 1 plus S by P1 into 1 plus S by P2. So can you tell me what is the DC gain here? I mean, okay, A0 is the DC gain in terms of the parameters, yeah. GM1 by G1 times, not G2, I mean total conductance is GL prime, right? Okay. Right, okay. Similarly, can you tell me the first pole approximately? The conductance here is G1 and the total capacitance is approximately this capacitor multiplied by the second stage gain. So it's G1 by roughly CC times. Okay. Similarly, what is the second pole approximately? Again, first let's write it fully. So if you write the total capacitance, we have these two guys, which is CL prime, in parallel with a series of C1 and CC. So that's CL prime plus and if you look at the conductance, what is the total conductance we have here? We have GL prime and this feedback around the GM that also presents a real impedance, which is GM2 times. Okay. Right. And here, as we saw, if GM2 is typically much greater than GL prime, so typically we can ignore GL prime in comparison to GM2, right? And in addition, we saw that if basically C1 is much smaller than CC and C2 is much smaller than CL, how can you further approximate this as? C1 is much smaller than CC, so what will this become? GM2. Similarly, what will the denominator become? This will become C1. CL prime is CL plus C2. I have assumed C2 is much smaller than CL. CL prime is roughly CL plus C1. That once again you can ignore this guy and then say it's okay. Again, it should make sense because the total capacitance here is dominated by the load capacitor CL. That's what we have assumed. CL is much larger, and even if you look at the conductance, what we are saying is CC is much greater than C1, right? So when we are calculating the second pole, which is a high frequency pole, we can assume that C1 is essentially like a short. That is basically compared to C1 and CC, around high frequencies, CC will present a short circuit, C1 is open. So in this case, what is the looking in resistance? I mean, if I have something like this, what is the resistance looking here if this is GM? I mean, this is basically same as your MOS transistor whose gate and drain are connected. Okay, so resistance is 1 by Gm, and that's why you also have the conductance as Gm2 here. If both C1 and Cc are comparable, then you'll have a small fraction. I mean, then you can think of it as whatever test voltage you apply, only a fraction of it appears. So fraction of Gm will contribute to the conductance. But if C1 is negligible compared to Cc, it's as though you have direct short from the input to the output. It's okay. That's what happens at high frequencies, and that's why the high frequency pole is approximately Gm2 by the load capacitor. Similarly, we had an RHP0 which we computed it to be, I'll just say Gm2 by Cc. Okay. And what was the unity loop gain frequency? Or how did we compute the unity loop gain frequency? I mean, this is a higher order system. Yeah, we know that if it's well compensated around the unity loop gain frequency, it's going to mimic a first order system. So till around the unity loop gain frequency, I can approximate this as A0 by 1 plus S by P1. So the unity loop gain frequency is the feedback factor beta times the DC gain times the first pole. So this is approximate. This is in turn equal to beta times Gm1 by Cc. Okay. So remember, this is an approximate expression assuming that the OTA is well compensated. That is, it is behaving very good, like this is behaving like a good first order system till the unity loop gain frequency. Great. So here, if we try to sketch the Bode plot, let's see how we'll have. So let me sketch the magnitude of the loop gain. It starts from some DC gain A0. We have the low frequency pole. It falls as let me maybe do this, minus 20 dB per decade. So this is the unity loop gain frequency, which is beta times Gm1 by Cc. And you have the second pole and the 0 occurring after this. Now if I look at the expression, the second pole is Gm2 by Cl, the 0 is Gm2 by Cc. Okay. So if I assume the load capacitor is slightly higher than Cc, which will occur first? P2s will occur earlier than the 0. I mean, that is just an assumption I'm making. If not, you can have the other way. So I'll assume Cl is greater than Cc, so pole occurs first and then the 0 comes. Okay. So if I also sketch the corresponding phase plot, this is the loop gain. Remember, the transfer function has one RHP0 and two LHP poles. So the phase will start from 0, and where will it go to finally? Minus? No. I mean, for this entire thing, minus 270. Okay, two LHP poles each contributes to minus 90 degree phase lag. This RHP0 will in turn add one more minus 90 phase. So it will start from 0 and go to minus 270. So first let's qualitatively sketch it. So you have the first pole, it will drop, it will try to go to minus 90. Okay, let me maybe not sure. Minus 90. And then the second pole is occurring here. So the phase will start to drop somewhere here. And then do this. So let's say this is minus 90, minus 180, and it asymptotically reaches minus 270. Right? So at the unity loop gain frequency, we have so much as the phase margin. Okay. So one thing should be careful is, let me just copy this. So in this case, let us say assume that the second pole and the 0 occur earlier than omega U loop, right? So let us say I have this, second pole occurs here, and let us say the 0 occurs here, right? So even now, what will be the slope around unity loop gain frequency? But is the system stable? Huh? Yeah, I mean, remember what you have to look for stability is not this. Around the unity loop gain frequency, you should check the corresponding phase, right? And how do you think the phase will look like? It starts to drop, but the second pole is occurring here, so it will do like this, right? It will drop much earlier. So here, what will be the phase margin? I mean, it's 0 basically. I mean, like negative, right? I mean, I've drawn it very badly, but let's say, okay, to do a lot of undo. Something like this. Okay, so around this, we have, like very poor phase margin. So it's indeed unstable, right? So don't blindly just look at the magnitude plot. So it is true that we want the system to behave like a first order system around unity loop gain frequency. But that doesn't mean that only the magnitude plot should exhibit minus 20 dB per decade slope, right? Significant information is actually present in the phase plot, okay? And in fact, if you recollect, when we are looking at the effect of pole, let us say we have a system like this. If I sketch the magnitude plot for this, in the Bode approximation, we'll have this and then do this. Right? I mean, if you sketch the actual frequency response, we'll have a 3 dB drop around the pole frequency, right? And if I sketch the phase plot, how will the phase look? What will be the phase value at the pole frequency? I mean, first order system, phase will start from 0 and go to minus 90. But at the pole frequency, what will be the phase? Minus 45. Okay. So the phase will look like this. So as you can see, around the pole frequencies, the magnitude plot shows very minor variation, right? But if you look at the phase plot, it goes from 0 to minus 90. But half of the phase is added even at the pole frequency. Okay. So the bottom line is the effect of pole or a 0 is much more visible in the phase plot than in the magnitude plot. Right? So simply just don't only look at the magnitude plot. Phase has even more information than what the magnitude plot can give you. Okay. Cool. So yeah, now we have looked at this two-stage Miller compensated OTA at a block level. Now let's put everything in terms of transistors. So here we have a first stage which takes in 2 inputs and gives you 1 output. What is a possible candidate for realizing this? The 5 transistor diff amp or any kind of cascode you want. The second stage takes in 1 input, 1 output, common source. So let's try to replace everything. So I'll first draw the first stage. I'll take an NMOS input diff pair, but you can do the same thing with the PMOS input also. So I have a PMOS current mirror here, the NMOS diff pair, and then the tail current source. Fine. You guys know this already, so let me label these guys. So this is the first stage. Let's say it's biased to provide a current of I0. Now we have to have the second stage. So second stage is what configuration? It's a common source. So once again I can have 2 possibilities. I can either have an NMOS input common source or a PMOS input common source. Which do you think is better? Why? Yeah, why?
That would be like similar to this now.
Yeah. See, I think you guys are getting it. So, with respect to small signals, is there any difference? No. So, if there is any difference, it should come from DC operating point and large signal behavior. So, as you guys pointed out, if let us say I apply the same bias voltage here for biasing it, what will be VD1 and VD2? they will be same. Again, we saw that although this is asymmetrical, if you apply a common mode excitation, it is symmetrical. So VD1 is VD2, and what will be equal to VDD minus VSG3 at a current of, right? So now if you try to have an NMOS here, and let us say this is supposed to be biased at some current I2, what should be the voltage here? I mean, the NMOS has to carry a current I2. The gate voltage is some VGS of the NMOS at a current I2. That's all. For this, what should be the voltage? VDD minus VSG of that PMOS transistor at a current I2. So now you can naturally see that the first stage is automatically providing a voltage which is more compatible to be used with the PMOS. So it makes sense to do that. So yeah, if you use a PMOS input diff pair here, then what would be a second stage? I mean, here I have used NMOS input, so it looks like second stage is better off with the PMOS. If the first stage has an PMOS input, second stage NMOS is a better choice, right? So let's do that. Oops. Okay. So I'll draw the mark it here. So I have the PMOS as the common source here, and ideally you want to have a current source. But how will I realize this current source? Yeah, I mean, I'll have to use a transistor. Which transistor? NMOS. So I can use an NMOS here and mirror the current from this guy. So let us say you want this to be biased at some current I2, and let me also label this as M5 and M6. So you choose the sizes of M0, M6 appropriately so that here the current is I0, here it is I2. Okay. And of course, this is two stage, so you have to put a capacitor to compensate. Let us put that. You see? Great. Good. Yeah. So now let's figure out what is the plus and minus terminals. So I know for a fact that this is the output. So let me say it is A and B. What is the positive terminal? Yeah, why?
Like if B increases.
Yeah, okay, let's follow the argument. Let's say if B increases, what happens to the voltage here? It decreases. Again, you are increasing the gate voltage, so you are pulling out more current from that node. The current here increases. If you pull out more current, that voltage drops. So gate voltage of M5 reduces. What happens to output? Increase. So again, if you reduce the gate voltage, you are pushing in more current into that node. So that will in turn increases. So B is positive. So yeah, this gives you a moral. Always be positive. Yeah. So yeah, now we have this. So let me copy this. So this guy is the negative terminal. This is the positive. I'll erase all this. Okay. So now let us say I go and apply a DC bias here. Say some common mode voltage to both the gates. So what do you think the output DC will be? This is the operating point, right? Basically, I have biased both of them at some common mode voltage at the input. What is the?
Can be anything floating.
Huh?
Need to fix it.
Yeah, he's saying we need to fix it. Anyone thinks it is already fixed?
At DC.
DC, just operating point, right?
You can tell minimum maximum.
Yeah, I mean, of course, you can find what is the minimum and maximum that you guys know. But the question is, if I apply, let us say, these voltages here and try to measure the voltage at the output, what will it be? Can you find it or no? VGS is fixed for M2, okay. But we are looking at output. What is fixing this voltage here? Is there something that is fixing this? Okay, see, this is essentially same as what we saw. I mean, I don't know if I talked about it. So we have a similar setup like this, where the PMOS is biased with some voltage, NMOS is biased with some voltage. Ideally, you want the same current to flow in both of them, right? So let me call, this as some INMOS and IPMOS. Now, of course, if there is minor mismatch in the two currents, so let us say, for example, INMOS is greater than the PMOS current, what will happen to the voltage Vx? It will keep decreasing. So what will happen? If Vx decreases, what will happen? NMOS can go out of saturation, it will enter triode, and finally that's how it reduces. I'll just say, which means NMOS enters triode, and that's how the NMOS current will finally reduce and the currents will eventually become equal. Opposite will happen if PMOS current is higher, right? So this is not a great way to have the circuit, because as I mentioned sometime before, this is like having two current sources in series and then trying to find what this voltage is, right? So ideally, if one current is greater than the other, this voltage will either increase or decrease, and even if they are exactly same, it is not clearly known what is this output, right? So you can't have two current sources which are independently biased, and you can't connect them in series. So typically you set one of them and then go and change the other based on the first current. Okay, so only one of them can be set independently. You make sure that there is some mechanism to tweak this current so that this current is equal to this. Okay, so you need some feedback mechanism, and in this OTA, finally, where are we going to use this guy in? I mean, why are we making this op amps in the first place? To be used in negative feedback. So let us say I go and use it in negative feedback. Let's say put it in unity feedback like this. So here I'll apply the input at the positive terminal. So without the input, some bias is applied. So then what can you say about this voltage? Yeah, because of the negative feedback, that will also be at VCM, and that is what will set the output common mode. Okay, is that clear? So here let's make the connection and see what happens. So we know the negative terminal. This is the negative terminal. So I'll go and make the connection. So I'll actually draw it neatly. So this is the positive, this is the negative. Okay. At the positive side, you are going to apply the, say, some VCM. And ideally, we also expect that this is also at VCM. Okay. And now you can see, if let us say the current in the transistor M6 is, let us say, ID6, this is ID5. Now we can check if what happens if, let us say, ID5 is, or ID6 is greater than ID5. What happens to Vout? Vout decreases. If Vout decreases, the same is fed back to the gate of M1. So which means gate of M1 decreases. So then what can you say about VD2? Basically what I'm saying is this voltage reduces. That is basically reducing this voltage. So what will happen to this? Increases or decreases? Okay. Okay, see, if gate voltage here drops, what can you say about the drain voltage here? Increases? So which means this gate voltage increases. So this one, are you guys following it? I mean, if I reduce the gate voltage, the current I am pulling out of that node reduces. So which means more current is getting pumped here. So this voltage will increase. For the PMOS, the gate voltage is increasing. What can you say about the current flowing? Current flowing will reduce. So then this voltage will, right? So if this voltage reduces, what can you say about the current ID5? That will increase. I'll say VG5 also reduces. And that's how the currents finally become equal. Is that okay? So here this negative feedback will make sure that the two currents are equal. And here the current source that is biased independently is M6. Right? Here you applied a bias voltage independently. So that ID6 is equal to some current I2. And this overall negative feedback you have, that enforces the current in M5 also to be equal to this. Is that okay? Okay. And finally, we also expect that the because of the virtual ground, we expect this guy also to be at the same VCM. But let's verify if that is the case. Let me copy this. Erase all this. Okay. So what I expect is the output voltage must be equal to the same VCM you apply at the other input. This is what we expect. But we know that this negative feedback, what it essentially does is makes the current flowing in these two transistors to be equal. Okay. So the current flowing in the transistor M5 is equal to I2. So if the current flowing here is I2, what can you say about the gate voltage VG5? Yeah. So basically I'll say the negative feedback basically sets VG5 to be at an appropriate voltage so that M5 carries the same current as M6, which is I2. Is that okay? So VG5 will be set to VDD minus the required VSG5 at the current I2. Right? And as you see, that is what is connected to VD2 also. Okay. Now we assume that both these guys are equal, and we also know that if the two gate voltages are equal, right? And for experiment sake, let us say I don't do this, I just take the first stage alone. For the first stage alone, if I apply the same gate voltages here, what can you say about the drain voltages? They have to be same. We have seen it multiple times. So this will mean that VD1 must be equal to VD2. And this in turn must be equal to, what is VD1? VDD minus VSG3 at a current of, okay. But now this is the connection we are making. And here we see that VD2 is set to VDD minus VSG5 at a current I2. Right? That is what the negative feedback is setting this voltage VG5 to. Is that clear? Great. So, which means looks like there are two possibilities. If I don't basically connect this and I apply the same gate voltage here, I expect both drain voltages to be this. But if I connect the two-stage OTA in negative feedback, the negative feedback is setting the drain voltage VD2 to this value. So it means if this source to gate voltage of M5 at a current I2 is not equal to source to gate of M3 at a current I0 by 2, my VD2 will be set to this, my VD1 will be set to this. Right? Is this clear? So now you see that VD1 is no longer equal to VD2. If I design for this case. Okay. This argument okay? I mean VD2 is essentially, VD2 is the gate voltage of M5 and that is primarily set by the negative feedback loop to keep the current in M5 equal to I2. So that is what is setting this. And VD1 is set by this diode connection, which is whatever, VDD minus VSG3. And if the two VSGs are not equal, then VD1 is not equal to VD2. But we know for a fact that if the two gate voltages are equal, the two drain voltages have to be equal. Now you see the two drain voltages are not equal. So what should that mean? The two gate voltages cannot be equal. Okay, that is the only way this could happen, right? So this will not be at VCM. This will be VCM plus some delta VOS. So which means my gate voltage of M1, which is same as the output, is VCM plus some delta VOS. Okay, and this is called the systematic offset. Okay, and why is the systematic offset happening? I know, but what design choice has made us get this offset? Huh?
So what you're saying?
Okay, is this okay? I mean, this VG5 is set by the negative feedback to this value. VD1 is set to VDD minus VSG3 by this diode connection. Now, if the two source to gate voltages are not equal, the two drain voltages are obviously not equal. But I know that if the two gate voltages are equal, the two drain voltages have to be equal. So I'm just doing the reverse. If the drain voltages are not equal, which means the gate voltages cannot be equal. Which means although we applied VCM here, this will not be at VCM, it will be at some offset voltage. And that is what is called systematic offset. Now the question is, why is this offset coming? Why did this happen? Not current, but you are partially right. But why is this? I mean, these two voltages are not equal because the two drain voltages are not equal. And why are the two drain voltages not equal? Sorry?
Because I2 and I0 is not.
I mean, that need not be same. It is partially right, but I mean, you can't always keep the two currents equal. What is not exactly equal here? Yeah, it is this guy. It is because you have chosen the two source to gate voltages to be not equal, you are having this issue. Is that okay? So the simplest.
VG1 and VG2 are not equal.
Yeah.
And for MOSFET 3 and MOSFET 4, they have the same VSG. Then the current in those two branches won't be equal.
But you have the drain dependency also, right?
That's why I'm saying no. If VD1 is not equal to VD2 and both have same VSG, then the currents in those two M3 and M4 won't be equal.
M3 and M4.
The currents won't be equal.
Yeah, it won't be equal.
Can that like compensate this?
Not exactly, because you will find that drain dependency is not so much, gate dependency is more in the current, right? Current is strongly dependent on gate voltage.
Voltage has to change.
Yeah. So the simplest solution to prevent the systematic offset is to ensure this condition, that is, let me copy this. So this is the primary reason why the offset is happening. So to avoid this, you just choose VSG5 at the current I2 to be equal to your VSG3 at whatever current you have. Okay. And you know that VSG is basically square root 2 times I plus, right? So if if the two transistors are identical, threshold is identical. So if I have to keep the source to gate voltage same, what should I be keeping same? I by W by L, right? Okay. So I by W by L for the transistor 3 and 4 must be equal to and typically if you choose the lengths of the three transistors to be same, that simply boils down to having the same I by W for okay. Why not?
Keeping length only,
Yeah, what I'm saying is this is the ratio that needs to be same, but typically if you choose same lengths, what you have to do is keep the ratio I by W same. That's all. As you will see, typically we don't play around a lot with the length. If you want to scale a transistor, you scale the width. Okay, because scaling the width is simply meaning putting multiple things in parallel. That scales much better than scaling the length. We'll see it later, but yeah. And this ratio is called the current density. That is I by W is called the current density.
Earlier the source to gate voltages were different because we were assuming different currents with same W by L ratio. So we have to
correct. Yeah. We didn't assume anything, so it could happen that the source to source to gate voltages are not same. If that has to be same, you have to maintain this condition. That is, for the same current, you make sure the same current density is there. Is that clear? So bottom line, if you want to prevent systematic offset, you make sure that these three guys have the same current density. I will say I by W. That is assuming the lengths are same. Now, in practice, you also have something called random offset. We'll see later, but that comes essentially due to random mismatches in the transistors. This is not random. This is very systematic. It is because of the way you have designed it. Okay. So there is a clear distinction. And the lame analogy I give is, let's say you cook biryani at your home. Every time you cook, you follow the same thing, but due to some random changes, taste might be different every time. That is like random mismatch, right? But let us say you cook for yourself, but second time, let us say an unwanted guest comes to your home and he insists on you cooking for him. So intentionally add more salt, more water, overcook. That is like a systematic offset, right? So anything under your control, if something is coming because of things under your control, that is systematic. Random is something that is not under your control. Okay. Cool. And you can also quickly find out if you choose the source to gate voltages to be not same, you can find out what will be the offset you have. And for that, let me copy this. Yeah. So I know that if let me erase this fully. See, I know that the negative feedback is setting the drain voltage VD2 to be VDD minus VSG5 at a current I2. The other drain voltage, it is at VDD minus some VSG3. Okay. Now I can basically write my VD2 as the nominal value plus some delta V1, right? Where delta V1 is VSG3 minus VSG5. Okay, I'm not writing the currents for simplicity. Is that okay? So now we can think of the scenario as the following. Your drain voltage VD2 is at the nominal voltage. On top of it, you have a small delta V. And if we assume that this delta V is a small signal, now we can use small signal approximations. So you have an increment delta V1 at the output. What is the corresponding delta V at the input? Yeah, delta V1 is the increment you have at the output. Okay. That is happening because you have a corresponding delta VOS at the input. Now, if all the delta V are small, you can use your small signal approximations.
So GM1 times upon
Yeah,
plus GDS.
let's write that, right? So this is delta V1 is the gain times the delta V1, sorry, delta VOS. And what is the gain? GM of which transistor?
1 or 2.
1 or 2 times?
On or 4 times.
This is something you can do if the offsets are small, right? So now you see that the offset is essentially this delta V, which is VSG3 minus VSG5 by this large gain. So if the gain is large enough, typically this offset will be small. So if you are okay with that, you don't have to worry. But if you don't want that offset also, you have to choose the current densities to be same for all these. Okay, cool. So okay, what we can do, yeah. So now we know what is this. Yeah, so bottom line, if we have this OTAs, what is setting the output bias is this negative feedback you are going to have around the OTA, right? So you are going to set it at VCM, and if this has no systematic offset, this will also be set to VCM, right? And even if you don't use a unity feedback, if you have resistive feedback like this, even then we can check. So even here, ideally you connect it to ground, but in practice you have to connect it to the bias voltage, say some VCM. So which means if negative feedback is present, what will be this voltage? So now at the input you are going to give some Vn of t. There also you apply the same common mode plus your delta V, whatever, right? So with respect to the DC bias, this is also, if this is also at the same VCM, what is the DC current flowing? So what is the current flowing here? So what should be this voltage? So what is setting the output bias now? What is setting the bias voltage at the output? Yeah, the negative feedback you are having around the OTA is what is responsible for biasing the output properly. And the thing to notice, this negative feedback is present at DC, right? So this DC negative feedback is what sets the output bias. Okay. And for this reason, you would have seen this, right? So we have seen this circuit, right? What is this? What does the circuit do? Integrator. So do you think this has a negative feedback at DC? No, right? I mean, for DC, capacitor is open, so you don't have a negative feedback at DC, right? So if you actually go and put this will not work because nothing will be biased, right? And for this reason, you never find integrators used in open loop anywhere. It will always be part of some big negative feedback loop. So we'll have some global negative feedback around this, and that is what will set all the voltages here. Okay. Right? The point is, I mean, we say that the virtual ground property exists, but that is true only if the op-amp, the transistors inside the OTA are all operating in saturation region, giving a large enough gain. So which means there should be proper DC bias set, and that is possible only if we have a negative feedback at DC. Okay, and that is true especially for cases like what we have seen, where we have kind of two current sources like this. Cool. So just one last thing we'll do, then I'll continue. So now we have the two-stage OTA. Yeah, schematic is here. Oops. Go. Yeah. So what we'll do is this. Let's quickly write the pole locations once. Let me also draw the block level model we had. and compare the two. So GM1 intrinsic conductance is G1, capacitance is C1. This is the GM2. So this is G2 and C2, and then you had the compensation capacitor CC. So now let's say you want to connect the load conductance and load capacitance, right? Here also you'll basically go and connect the same, right? But if I connect it to ground, what will happen? I mean, let us say I have only a load resistor now. I connect this to ground. Is this fine or not fine?
Not fine.
Why?
Because that there will be current through RL.
Yeah, remember that finally let us say this is put in some DC negative feedback like this, right? And you have done it properly so that this is also at VCM. So the output DC nominally is at VCM. If you connect the resistor to ground, that is going to draw DC current. Your entire biasing will get screwed. So what should you connect the other side of RL to?
VCM.
Yeah, you don't want to have any DC current flowing through this. Okay. So all your load resistors you connect there. Capacitor it's okay, but I mean when I draw ground, these are all small signal grounds, right? At the block level, wherever we have grounds, incrementally there should be ground. You can connect it to any DC voltage and you connect it to an appropriate VCM so that there is no DC current draw. Okay.
RL, if it is short circuit, then full current will flow. Somewhat current will.
No, RL short circuit meaning the resistance is very small, right? It's up to you. You make sure that the load is other end of it is connected to here. If not, you have to put a like whatever a large bypass DC coupling capacitor and all that stuff, right? If you don't do this, then you have to make sure that the DC is something like this, right? You have to put a large cap here, and on ICs you don't want to do because large capacitors will take a lot of area. So simpler fix is to basically do this, right? You connect it appropriately. And see, this VCM, what is the range of voltages, right? You can calculate. You can have a range of voltages so that all the transistors remain in saturation. But typically, let us say the supply is from 0 to VDD, and your small signals is going to swing over and above the VCM. What would be a typical value to choose? Yeah, you typically choose it to be around the mid rail so that you can have maximum swings in the positive side and negative side. Although it's not necessarily the case, you can choose anything within that range you compute. This is a typical choice that is made usually. Okay. So yeah, before concluding, let's look at the pole locations once. So let me erase all this. Let me erase this. So here, let's say I have GL, CL connected to VCM. So first, let's map all these parameters to the circuit, the transistor properties, right? So what is the short circuit GM1? I mean, this GM1 is provided by which block here? It is basically GM of transistors 1 or 2. What is short circuit GM of the second stage? Second stage is this guy, which is providing the trans conductance. GM5. So similarly, if I find the intrinsic output conductance at the output, what is it? Yeah, R02 parallel R04. So conductance is GDS2. Okay. Similarly, what is the intrinsic conductance at the output here? GDS6 plus GDS5. plus GDS6. Okay. So what is the parasitic, I mean, which all contributes to the parasitic capacitance C1 here? C1 is here, right? What are the parasitics contributing to C1? This is connected to, basically you see which all transistors is it connected to? It is connected to first M2. Which component of this will first? Drain to bulk of 2 will come. Similarly, drain to bulk of 4 will be there. And what about M5? You have gate to source of M5, right? And you will also have something due to the CGD of M4. It's not trivial, but see, finally the thing is, in a MOS transistor, which of the parasitic capacitance is usually the highest? Gate to source, right? So typically this will be completely dominated by CGS5. Okay. So what is C2? It's a parasitic capacitance from here to ground, which is drain to bulk of M5, drain to bulk of M6. Okay. And you guys know the pole locations, and you have an RHP0 that is directly from here. But remember that I have this 5 transistor OTA. This guy has been approximated as a first order system here, right? But you very well know it is just an approximation. This guy also has additional pole. So what is the additional pole this guy will add? You will have a parasitic capacitance here, let us say C3. So what is the pole contributed by that? GM3 by C3. And is there something else? If you recollect, you also had a 0 from this guy. That was at, yeah, that was at twice that frequency. Okay. Nice thing is this was an LHP0 actually, right? Which one? GM3. Oh, so, no, GM3. This transistor, right?
No, for the 0.
No, okay. The thing is, you have a 0 from the block level thing, that is capital GM2 by CC.
No, for Z2.
Yeah. Z2 is coming from this only. If you recollect, the 0 from this was at twice this non-dominant pole. Okay.
That was the pole that was getting cancelled. 2 GMP.
No, that is a different thing, right? You had an extra pole here that was getting cancelled by a 0 in the differential mode. But here, if you recollect, in the 5 transistor OTA, right, I'll just roughly draw. So if you find the thing, you have two paths, right? You have current coming from here, and you also have current coming from here. And this is an extra capacitance here contributing to a phase shift, and that added to a 0, and if you recollect, the location was this. So bottom line, you no longer have the 2 poles and the RHP0 that you computed from this model. You also have the other non-dominant pole coming from the first stage. So if you actually design for a particular phase margin, at a block level, we expect the phase margin to be 90 minus tan inverse the second pole and the phase added by the RHP0. But now, because of the presence of this additional pole, you will have some degradation in the phase. But typically it might be okay because this is immediately followed by a 0 at twice that frequency. It won't be that significant, first of all. And secondly, if you compare the relative positions, this is at GM3 by C3. Where is the second pole here from the block level? GM2 by CL. Let's say it's CL. So now you know CL is going to be a load capacitor which will be typically much higher than the parasitics. If that is the case, this non-dominant pole is already occurring at a lower frequency than this. or in other words, the additional pole that is coming because of this guy is occurring at a much higher frequency than your non-dominant pole. So typically it's okay. But you should have it in mind that if that is not the case, this guy can introduce an additional phase lag. So the phase margin can be slightly smaller. Just have it at the back of your mind. Okay. So I'll stop now.